Okay, in this video I want to talk about the rules for using curved arrows. Now these curved arrows or curly arrows are used for electron accounting. We know that since electrons are a form of matter, they themselves are conserved in a chemical reaction. They can neither be created nor destroyed. In organic chemistry, you have movement of electrons, like the tide of an ocean. They move this way, then that way, and they ebb and flow, and they move, and then finally something pops off in a negative charge, or a bond forms, or there's all kinds of weird stuff in organic chemistry. And so we got to keep track of that with curved arrows. Curved arrows can be just drawn like so. They sometimes can be really curly or whatnot. We try to make a curve to them so that we don't confuse it with a reaction arrow or a resonance arrow or an equilibrium arrow. These are different arrows. Now, I'm not going to show fishhook arrows, which show the movement of one electrons. I'm going to show these arrows here, which show the movement of two electrons. So if we have a curved arrow, we call this the foot of the arrow, and we call this the head of the arrow. Okay? And generally speaking, you have curved arrows that go from one atom to another. And so, for example, if we have two electrons here on atom A, and let's say it has a negative formal charge, and we have atom B, which has a formal charge of plus, we can show a curved arrow. I'm going to use red now for all my curved arrows. If this curved arrow, it's basically a movement of two electrons. Now we can just draw it like this, pointing to the atom. We can also, as I'm explaining to you for the first time, lasso them up. Okay, so pretend like this is a rope, and we're taking those two electrons, and we're pointing those arrows to B. Now technically what we're doing is we're moving those two electrons right here. So this is a reaction arrow here, so A has electrons and they're going to move to B, and what you're going to do is form a bond between A and B, and the formal charge goes away. All right, so these two electrons here literally get placed into this bond. So those two electrons now are between atoms A and B. Okay? And formally charged speaking, A lost one electron and B gained one electron. So that's a bond. I'll draw a line over these electrons here. Okay? So that's a new bond. So rule number one, you can kind of see that when electrons point to an atom, so when the arrow points to an atom, a bond is formed. All right, and that's very, very important. So let's look at some real life chemistry here. We're using A's and B's, and this might not be too good for you. So let's look at some examples. So let's say we have chloride here. Now chlorine with no bonds and 8 electrons is a formal charge of negative. And let's draw a simple, very simple molecule. This molecule here has a carbon with only 3 bonds and no lone pairs, so its formal charge is +1. This is a carbocation. And in red here, we want to show the movement of electrons. And you can draw the arrow coming from the negative or the electrons. I'm going to circle these just to be over-explaining. And I'm going to draw these pointing to, you can point to the positive or you can point to the carbon atom. Let me point to the carbon atom there. And so what do you get from this chemical reaction? You get a chlorine bonded to carbon. Where did those 2 electrons go? Those 2 electrons that I lassoed up with the circle there are actually in this bond now. Okay. And here's where I want to emphasize the rule number 2. Okay. Rule number 2. Okay, it's very, very important. I mean, this is like equally as important as rule number 1. But so what you'll notice is that the curved arrows keep track of what bond is going to be formed, and later we'll see what bond is broken. But it keeps track of formal charge as well. Now, the formal charge, so the foot of the arrow, so basically it's the atom at the foot of the arrow. It becomes more positive by 1. Okay? So if you look over here, we have Cl with a negative, and it becomes a negative and a positive becomes 0, right? So chlorine becomes more positive by 1 unit to become neutral in formal charge in the product. And so that's the foot, okay? And the atom at the head is going to become more negative. Okay, more negative by 1. And so if we look at the carbon, carbon is plus, and it becomes, you add a -1 charge to that, it becomes 0 over here. So the curved arrows keep track of what bonds are being formed and also the formal charge. You never have to refer back to that formal charge table to figure out, oh, carbon with 4 bonds has a formal charge of 0. You just look at the arrows, oh, it's pointing to it, so it's going to become 0. Okay, let's look at one more example here to introduce the concept of curved arrows. And here we're looking at reactions, which is fine. So let's look at a chemical reaction here. In the organic chemistry class, you always want to circle your formal charges to not confuse it with a plus from a chemical reaction. All right, so your question might be, draw the products of this chemical reaction after you discuss acids and bases. So electrons flow from where they are to where they are not. H plus has no electrons. Where are there electrons in this molecule? Non-bonding electrons are available for chemical reactions. So these 2 electrons on oxygen are going to swoop in and attack or combine or react with the H plus here. And what you get as a product is a bond between the oxygen and the hydrogen. Now these 2 electrons that I didn't circle remain fixed on that oxygen. And let's think about the formal charges now. Okay, let's think about the formal charges now. The foot, right, the foot of the arrow is going to become more positive. So here it starts out with a charge of 0, so it becomes more positive, so it becomes plus over here. So we want to put a formal charge of plus on that oxygen. And let's look at the head of the arrow. The arrow is pointing to H plus, so the head of the arrow becomes more negative by 1. So here it's plus 1, We add a -1 charge to that, it becomes 0, so we don't do anything with the hydrogen. Okay? So that would be that chemical reaction. Okay? Now, I want to talk about Rule 3. Okay, Rule 3. Now, when the foot of a curved arrow comes from a bond, not an atom, a bond, that bond is broken. And we still use the head, the foot, to keep track of formal charges. So let's look at a real live example of this. Let's look at this molecule here. Okay. And we want to take the 2 electrons in this bond. Remember, a line is a bond. It's 2 electrons. And I can put the dots on there, and I can circle this so I really know what is going on here. And also, if it's confusing to you, you might add lone pairs on the chlorine. Okay, so expand out the Lewis structure a little bit on your molecule. And so what we're going to do is break this bond by taking the electrons from this bond and moving them to the chlorine atom. And let's go ahead and draw a reaction arrow now. And let's draw the fragments that we have. So we're taking the foot of the arrow from that bond, so it breaks. So that plus just means and, right? It's not a charge. And then let's go ahead and add electrons and fill things in here. So those 2 electrons in red, I moved them to chlorine. To be ultra dramatic here, I will put those 2 dots there on chlorine. And now you can see how just by cursory examination, that's a formal charge of negative. Or you can see how the head of the arrow is pointing to chlorine, so it's going to end up to be a formal charge of minus. Now, what about the carbon? The carbon, it's losing those red electrons, so it has nothing, and the foot of the arrow is going to create a positive charge on that carbon. Okay, so that's an example of a bond breaking. Okay. And so you can have bond formation or bond breaking, and you want to be careful about which way the bond is breaking. Now, you can also break a pi bond. Be aware of that. Let me show you how that might work. Say, for example, you have something like this, formaldehyde. Okay. And we're going to write H plus towards the top here. And what we're going to do is grab just these pi bonding electrons. I can't really lasso that. I don't have quite enough room. And so we'll start doing this in the pro way without circling all of these electrons. And so what's going to happen here is that this hydrogen-carbon bond is there. I didn't move any electrons from that. This one's the same. The green bond, that I didn't touch, it's not changed. Now, where do these red electrons go? The red electrons are going to be forming a bond between the oxygen and the hydrogen. Okay, so I'll just draw it with a green pen, I guess. So, here's the new bond that you're forming. And we'll put the red dots on top of that bond so you could know exactly where those 2 electrons go. So you could think of this as being like a windshield wiper. Right? These electrons in this bond swoop over to make these electrons in this bond, okay? All right, now what about formal charge? The foot of the arrow is going to become positive. The head of the arrow is going to become more negative. So what's going to be positive is the oxygen, the carbon atom. Now let me show you why. You see, in this structure here, we have a bond, 2 bonds to oxygen, right? 2 bonds to oxygen. So it has a formal charge of 0. And here we have 2 bonds to oxygen. So its formal charge is equal to 0. All right? So when you have this kind of like windshield wiper effect, there's still the same number of bonds on the oxygen. But where the electrons are being removed from is the carbon atom down here, okay? This carbon atom here is changing from 4 bonds to 3 bonds, and because that's where the electrons are ultimately flowing from. Oxygen is just kind of playing hot potato in the middle. So what we do want to show is a positive charge on this carbon, okay? Oxygen has 2 bonds, hydrogen has 1 bond, so everything's fine there, okay? Let's look at another example where you have an atom in the middle that does not change. Let's look at an acid-base reaction between this organic alcohol and HBr. Okay, so let's go ahead and grab our things here. And I'm not going to circle the electrons. I'm going to take these lone pairs on oxygen. Okay. And we're going to do a sequence of things. Okay. So again, the rule is that if you point to an atom, you're going to make a bond. So we want to make a bond between the oxygen and the hydrogen. Okay. I'll fill in lone pairs and charges later. And then the rules state that if the curved arrow comes from electrons in a bond, that bond is going to break. So the HBr bond breaks, and we have just Br floating around. And what do we want to do is we want to place, I'm not going to draw lone pairs at all, okay? So I want to keep you advancing in the course. We're going to use electrons kind of loosely at this point. If an arrow comes from the atom, it becomes positive. And if the arrow points to an atom, it becomes negative. So that's it, we're done. Okay? Hydrogen, what's happening with hydrogen? Why does hydrogen not change in charge? Because we have one arrow pointing to it and one arrow coming away from it. So like I said, it's kind of playing hot potatoes. It takes those electrons from oxygen, holds them for just a bit, and then hands them off to bromine. So it doesn't, at the end of the reaction, have more or less electrons. Okay? So that's a brief introduction to curved arrows. There might be other situations that you encounter. That are a combination of bond breaking and bond forming with a pi bond. So, for example, if we want to take these 2 electrons in the pi bond, okay, and point to the hydrogen, and that comes off, what do we get from this chemical reaction? Well, we would say that first connect every atom together that is being instructed to us by the use of these curved arrows. So all of these CH's bonds are there, right? And then attached to the top carbon, we're going to have an additional hydrogen because the arrow is pointing to that H. And then the arrow is coming from a bond, so what we have floating over here is going to be H2O, or you might recognize that as water with a formal charge of 0. Now let's look at the formal charges. This carbon down here is electron deficient. It has electrons being removed from it. It's from the foot of the arrow, okay? And there's no pi bond there that we should draw. And the arrows point to oxygen, so that oxygen is going to be neutral, so we just leave it there. So that's that, okay? Sometimes you can have very complicated examples of 2 or 3 or 4 electrons all happening at once. Most curved arrows or most reactions or curved arrow reaction mechanisms can be shown in 2 to possibly 3 steps, okay? We don't want to draw too much happening all on one structure. You know, I see sometimes people try to draw a little bit too much at once. They draw, you know, well, I'll use the red pen. I'll use the red pen here. They draw things like this, and then they're trying to just draw too many steps all on the same, you know, thing, and they draw the product, you know, over there, or try to draw the product, and that's usually unclear. You want to not use so many arrows. If you're using more than 3 arrows, something's wrong. See if you can show it in discrete steps, okay? So in summary, those 3 rules here are as follows, right? So when the arrow points to an atom, a bond is formed, okay? So that's a very good thing to remember. And there's 2 rules for figuring out the formal charges. When an atom at the foot of the atom at a foot of an arrow becomes more positive by 1, and the atom at the head of the arrow becomes more negative by 1. Sometimes it's easy to figure out, and sometimes it's part of a pi bond, so it's a little bit more tricky to figure out, well, what is the foot of the arrow? Is it the carbon or the oxygen? Okay, and so you have to be careful about that. Number 3, when the foot of a curved arrow comes from a bond, that bond is broken. Okay? I did forget to, well, I think that's it. Yeah, I've summarized everything there, okay? So that is the review or the introduction of curved arrows.